Okay, good morning. Welcome to the second day of VMCAI'. We have our second keynote speaker, Hiroshi Unno. He got his PhD in Tokyo, University of Tokyo, 2009, continued in Tohoku University, sorry for mispronouncing it, and back to Tokyo, and now he's in University of Tsukuba in Japan. His research interest spans most of the VMCAI topics, I think, a lot of things. So automated software verification, synthesis, constraint satisfaction on optimization, automated theorem proving, type systems, functional programming, applications of machine learning and verification and synthesis. And today is going to talk about automating relational verification of programs.
Okay, thank you for the kind introduction, and thank you for having me. Thank you for coming. Okay, it's my honor to present my ideas and thoughts on relational verification. Relational verification is verification of properties that relate multiple execution of one or multiple more programs. And Clarkson and Schneider formalized such properties as sets of program choices and coined the term hyperproperties. And K-safety is a notable subclass defined as a hyperproperty that can be refuted by observing K-finite traces. And relational verification is an important trend in formal method with applications including security. So I first show you some examples. Example hyperproperties first on multiple programs. A prominent example to safety is program equivalence. There are variants of program equivalence. Let me start with functional equivalence, that is input-output equivalence. The terminations insensitive version is defined like this. It says if f of x returns some value y1 and g of x returns some value y2, they must coincide. And the termination sensitive version further requires that if f of x has a diverging execution, then g of x always diverge. Please note that this definition requires determinism. So it's too strict for non-deterministic programs. So a relaxed notion of equivalence can be defined as well, where the termination sensitive and non-deterministic equivalence can be defined like this, which it compares the set of possible outputs for the given x. Okay? And the probabilistic version of equivalence can also be defined using the probability distribution of the outputs. And for reactive system, we often use trace equivalence defined using the set of finite and infinite execution traces of programs P and Q. And bisimilarity is also often used, which is defined like this. There is a strong bisimilation R such that P and Q is in the set. We also have, there is much work on observation equivalence, which says for any context C, C in P, if C in P evaluates to Y, if and only if C in Q also evaluates to Y. This notion captures non-trivial interactions between context C and higher order object-oriented and effective programs. And in security applications, attackers' capabilities are reflected in the definition of context. Okay, and let me next explain program refinement, which is the one-sided version of program equivalence. Let me start with functional refinement. Termination insensitive version of refinement is defined like this. If f of x returns y, then g of x returns y. And this is useful to transfer properties and proofs of programs to the other one. So if this holds, then we can transfer the partial correctness of Z to that of F. Okay? And the termination-sensitive version, which further requires that if F of X diverges, then Z of X diverges, which preserve the total correctness properties. For trace refinement, it preserves trace properties of Q, which can be transferred to P. And similarity, which is defined like this. There is a strong simulation R such that P and Q in R. If P and Q are related by this similarity, then trace properties can also transfer to from Q to P, but branching time properties cannot be transferred. By contrast, we can use bisimilarity to transfer branching time properties of Q to P. However, hyperproperties themselves cannot be transferred by using the bisimilarity. And as far as I know, there is no automated approach for synthesizing some program refinement that can transfer, that can be used to transfer hyperproperties, which is interesting. If you know some work, please let me know. Anyway, let me move on to the next slide. This slide claims that program refinement is a generalization of ordinary model checking. Program refinement verification generates ordinary model checking in the following sense, where a specification of P is given as a program Q instead of some logical formula phi. Q can encode the given phi if the language is expressive enough. Furthermore, Q can be a reference implementation or an abstract model represented as a highly non-deterministic program. Okay. And this motivates me to investigate entailment checking problems in a very expressive logic of first-order fixed-point logic module theories we call mu-CLP, and which is discussed in these papers. I will come back to this point later, relational verification via entailment checking in mu-CLP. And let me next show you some example hyperproperties on single programs. A killer application of relational properties is information flow, confidentiality, and integrity. For deterministic programs, there is a definition called termination insensitive non-interference, which is to safety, defined like this. Now, program F takes high security inputs H, and the definition is like this. For any high security inputs H1 and H2, and low security input X, and low security outputs Y and Y2, if F of H1X returns some value Y1, and F of H2X returns some value Y2, then they must coincide. This is a well-studied security policy formalizing the absence of information leakage from high security to low security. And the termination-sensitive version of non-interferences further requires that for any H1, H2X, if F of H1X diverges, then F of H2X always diverges. Okay? And we can also express timing attack resilience as a hyperproperty, but I will not go into details. For non-deterministic and concurrent programs, we can define other notion of other variant of non-interference, which is possibilistic non-interference, defined like this. Termination insensitive generalized non-interference is defined by this. It says that for any H1, H2, XY, if F of H1X returns some value Y, then F of H2X either diverges or returns the exact same value Y. Okay? The termination-sensitive version is simpler, which omits this condition. And we also have bisimulation-based non-interference, but I will not go into details. Okay. And also, availability policies can be expressed as a hyperproperty, but I will skip this one due to time limitation. And algorithm analysis, robustness and sensitivity can also be expressed as hyperproperties, which I will not go into details. So yeah, let me skip it. And let me finally explain some specific use cases of hyperproperties. The first one is regression verification, which checks that the given program T is a refinement of the other program S for different versions T and S, where T is obtained from T is obtained from S by refactoring, bug fixes, or enhancements. And goal is to verify the absence of a software regression, that is a bug of T introduced by the modifications to S. Other useful cases are translation validation. It checks that T is a refinement of S for the source S and target T programs obtained by compilation or optimization to validate the translation. Okay. Other specific use cases include verification of an implementation of an abstract data type with algebraic specifications. For example, arithmetic operators such as mult and sum can be verified with respect to the algebraic specifications like equivalence, associativity, commutativity, distributivity, and so on. And please see the right table from my Cabot 17 paper, which proves our tool can automatically prove such properties of mult, sum, and other functions. And another example is verification of list operations with algebraic specifications. Our tool can automatically verify property like this, which says that, appending list. So take XS and takes the first n elements of XS list, and drop XS and drops the first n elements of XS. And by appending them, we obtain the same list XS. Our tool can automatically prove it. All right. So let me set the goal on my talk, rest of the talk. Goal is to stipulate the, in my opinion, immature research field and hopefully find new research collaborators. I'm going to discuss the challenges in relational verification and introducing our automated relational verification method and highlighting the current limitations as well as future research directions. And here is the disclaimer. This talk will mainly deal with fully automated deductive relational verification and target functional properties. I will not address trace or contextual properties, and I will focus on infinite state systems that can exhibit effects such as non-termination and non-determinism, and will not cover other effects or finite state systems. Okay? And this is the outline of the rest of the talk, and let me next explain challenges in relational verification. Although each program execution is independent in relational verification, proving relational properties is challenging without reasoning about the correlation of intermediate execution traces. So analyzing each execution separately doesn't work well, as it necessitates an exact summarization of the input and output relation for each execution. Thus, an automated verifier is required to simultaneously synthesize the correlation of intermediate states, we call relational invariant, and a scheduler, or people call alignment, that preserves it. Okay? And let me briefly compare relational verification with concurrent programs verification. In concurrent programs verification, executions of programs that run concurrently can be highly dependent. States can be synchronized with locks or semaphores, and data race can occur due to shared memory. So in concurrent verification, concurrent program is checked to satisfy the specification for all possible interleaving execution under a demonic scheduler. By contrast, in relational verification, multiple executions are independent, except for the inputs correlation. And it is sufficient to prove that the specification holds in a certain interleaving execution chosen by an angelic scheduler. However, to reason about the correlation between states at the time of output, it is still necessary to effectively synchronize other intermediate points as well. So therefore, the complexity of the verification is more significantly influenced by differences between programs. Okay, and let me use a program equivalence example to illustrate this point. These are two versions of multiplication functions. Okay, the first one, takes integer x and y and returns the multiplication of x and y. The second one is an optimized version of the first one, but the two are functionally equivalent. Here is an example execution of the first program, starting from 3 and 4, 3 for x, 4 for y, and returns 12. By contrast, this is an example execution of merge2, and with the same input, the same output, but the lengths of the execution steps are different. So let's align the executions to preserve this property that we want to prove as much as possible. The initial states must be aligned. And next step, we can execute them in lockstep and obtain these states, which satisfy the property. The next step, though the structure of program at the program location B and E are different, but anyway, we can execute them in lockstep to obtain, to preserve the property, and we can again execute them in lockstep. Then the equivalence is broken. Okay. We can, however, recover the relation by using a stutter execution, by just scheduling the first copy, mult1, to recover the property. And in general, we have to perform stuttery execution when this condition holds. Otherwise, we can execute them in lockstep. By using this alignment, we can, in fact, obtain a relational invariant preserved by the scheduler, which is sufficient to prove the property we want. However, how to infer such predicates, which is a challenge. In this example, we can obtain a predicate like this from the, extract it from the second program. But in general, we need to synthesize some useful predicates. So fully syntactic approach might not work here. Okay. Other example. Let me show you another example, termination insensitive no-interference. Let us consider this program, double square, which is obtained from this CAP paper, which computes 2 times x squared in 2 different ways depending on the high security input h. And so a question here is, can an attacker infer the value of h by observing the low security input x and the return value of y? Actually, this program satisfies termination insensitive no-interference, and attacker cannot infer the value of high security input. The property is defined like this, and let let us try to prove this one. However, first let us try the partial lockstep scheduler. Starting from so these are example execution traces. And please note that the low security input values x and y are equivalent. However, we assign different Boolean value to a high security input. Here, so preconditions, this one, x1 equals to x2. And by executing them in lockstep, we obtain these states which satisfy the property we want to prove. And again, a lockstep execution preserve the property, again preserve the property, but please note that here, copy 2 has exited the loop. And partial lockstep scheduler waits for copy 1 to exit the loop to synchronize. But this property no longer holds, violated. And so we cannot prove that this holds at the end. So natural question here is, if there are any simple but safe and inductive relation invariant preserved by the partial lockstep scheduler. Actually, the answer is no. There is no safe inductive relation invariant for the scheduler expressed in LIA, which is proved in this paper for this particular example. So in general, we need to come up with a clever scheduler. Okay. Let me next explain a code termination example, which is a hyperliveness property. Given these two programs, we want to verify that program 1 and program 2 agree on termination under the precondition, this precondition. Okay. So actually, these programs co-terminating. Co-termination can be formalized like this, and so this symmetric co-termination problem can be divided into two asymmetric co-termination problems. So let us prove an asymmetric version of co-termination. Let us try to prove it. So these are sample example execution of the two programs, starting from the same state. The first one, so in lockstep execution, like this, please note that the second program terminated before program 1. And we don't know how can we prove that this residual execution of program 1 always terminates. We need to solve this problem. And I will later explain how our method can deal with this example. Okay? And the last example is generalized non-interference, which is for exist hyperproperties. So this program non-deterministically returns a value x, which is greater than or equals to L, low security input L, but in two different ways depending on the high security input H. So they behave similarly, but the programs are different depending on the high security input. A question here is whether an attacker infer the value of H by observing the low security input L and the return value X. Actually, this program satisfies termination insensitive version of generalized non-interference, and attacker cannot infer information for high security inputs. Generalized non-interference is defined like this. Actually, this program also satisfies termination sensitive version of generalized non-interference. Please note that here, x1 in the definition is chosen demonically, while the value x2 is chosen angelically. So we need to somehow solve such games between universal and existential quantifiers. We also need to handle this problem. I will explain later how our method deal with this example. And there are other challenging examples in the literature which I will not go into details, but this program has loop tidying, this has loop splitting, and this one. Please note that the inner loop of the first program is summarized by this single statement, which is a bit difficult to handle automatically. And as far as I know, there is no single tool that can solve all of them. Anyway, okay, let me next talk about how to automate relational verification. Okay. There are two approaches, self-composition and end-term checking. So I will explain my previous work published in CAP'21 and 70. And maybe due to the time limitation, I will skip most of the second part. But anyway, let me start with self-composition approach. Self-composition refers to a range of techniques aimed at synthesizing alignments represented symbolically as programs, automata, logical constraints, and games. There are many, many works. I listed some. And in my opinion, there are two approaches. One is syntactic one. Syntactic self-composition tries to use syntactic program structures and types to find interleaving alignment as a pre-processing for precise verification. And by contrast, semantic approach to self-composition tries to simultaneously synthesizing schedulers and inductive relational invariants within a verifier. So for alignment synthesis, we can use information obtained during analysis of programs to find a precise value-dependent alignment. And yeah, I will explain our approach to semantic self-composition. We soundly and completely encode the simultaneous synthesis problem relational invariants and fair and semantic schedulers needed for relational verification and represented as a constraint solving problem of the class we call PFWCSP that extends CHC's constraint home clauses with these new features. And here, head disjunction is used to express scheduler fairness constraints, and well-foundedness constraints are used for synthesizing co-termination witnesses, and functionality constraints are used for synthesizing winning strategies for generalized non-interference. Actually, we generalize semantic self-composition for K-safety presented in this previous work by others to GNI and co-termination. And for solving the extended class of constraints, we provided constraints over PCSAT based on the templates-based CGIS and answered core-based template refinement. So let me go back to the previous example of proving termination insisted with non-interference. Here, let me explain semantic self-composition for the TINI example. Our goal is to find a semantic scheduler as well as a safe invariant of the parallel execution of two copies of the program under the scheduler. And so by semantic, I mean schedulers can choose which programs to execute depending on the states. And our tool, in fact, synthesizes this scheduler, which states if this condition holds, then both copies move. And if this holds, only the first copy moves. So these are the example execution traces. Let us try to align them with the scheduler, starting from the initial states. Because the first condition holds, we schedule both copies, and we align these two. And please note that here, this relation holds. Y1 is 2 times Y2. But next, we can again schedule both copies and obtain this property. But now, the first condition doesn't hold, and the second condition holds. So we only schedule the first copy to obtain this alignment. Then we recover the first property we had. And we can repeat this one. Next, we recover this one, and this one, and we can repeat this. And finally, we can show that this holds, and at the end of the program, we recovered this property that we want to prove. So this, for this scheduler, our tool synthesized. Our tool also can simultaneously synthesize this invariant, relational invariant, which is expressible in linear integer arithmetic. This is automated. Okay, and let me briefly show you how the synthesis problem is reduced to constraint solving. But I will not go into details, so you don't need to understand all of them. Here, predicate variable I represent a relational invariant, unknown relational invariant preserved by a semantic scheduler. And this part requires that the relational invariant is inductive and implies the property we want to prove. And this one, SCH predicate variables that represent the semantic scheduler. And if SCH1 holds, then first copy is scheduled. And these constraints represent the fairness condition of the scheduler, which says that at least one unfinished program must be scheduled if there is any unfinished one, which is necessary for soundness of our approach. Okay, right? So we encoded this fairness condition using an extension of CSCs. Okay, let me next show you how to handle asymmetric co-termination using our semantic self-composition approach. Our goal is to find a fair semantic scheduler and relational invariant, and furthermore, we need to synthesize simultaneously well-founded relation to witness co-termination. For the example execution, so for these programs, our synthesizer automatically finds this scheduler, which is actually a trivial one. It says that if both programs are still running, then schedule both of them. And the second condition says if the first program is still running, but the second terminated, then only program one moves. So starting from the initial state, we can execute them in lockstep. And here, program 2 terminated. Difference from the previous scheduler is here. We can find well-founded relation that says that if program 1 is still running and program 2 is terminated, then program 1 repeatedly decreases x1, but x1 is lower bounded by 0. We can what to automatically synthesize this well-founded relation, but we need a relational invariant to support this claim, which is represented by this one. This says that if program 1 is still running and program 2 terminated, then the value of y1 must be greater than or equals to 1, which is actually a relational invariant preserved by this scheduler. We can use this invariant to show that when program 2 terminated, then program 1 eventually terminates, because program 1 always decrement x, the value of x. Okay, so let me next move on to the, so yeah, this is how we reduced our synthesis problem to constraint solving. And again, I will not go into details, but briefly explain overview of the technique. Well, so I represent relational invariant and preserved by the scheduler, and we have this one, R down arrow, which represents a well-founded, unknown well-founded relation, witnessing the termination of program 1 relative to the termination of program 2. Okay? And these constraints require that the relation invariance is inductive, and along with the well-founded relation implies co-termination. And this part says that the scheduler is fair. In this case, fairness is defined like this. All unfinished programs must be eventually scheduled, which is a stronger notion of fairness compared to the previous one, and which is necessary for the soundness of our approach for co-termination. Okay, and okay, I will skip these details. And we also have, I will skip details. And the last example, semantic self-composition for termination insensitive, sensitive GNI. We need to find witnesses, fair semantic scheduler, relational invariant, well-founded relation, and also we need to synthesize strategies for the non-deterministic choices of the NGRX side. And so to this end, we augmented the encodings for TI and co-term with predicate variables that represent the strategies, Skolem functions, total functions from states to choices of the NGRX side. We also added prophecy variables that represent the final outputs of the demonic choice, demonic side, which was necessary for the completeness of our encoding. Okay, and so sorry, I will not go into details. Please refer to the paper if you're interested. And we have implemented the approach and evaluated on simple but small but very complex examples. And our solver, though it is not very efficient, but it anyway solved 15 out of 20 fully automatically, and only 5 required small hints. Anyway, so the tool PCSAT is a part of our core verification and synthesis tool chain, which I have been developing. And yeah, there are other tools, backend solvers and frontends, OCaml frontends, and so on. So please, if you're interested, please try to use it. And if you have any questions, please let me know. And this is, let me discuss the approach. Semantic self-composition has a high theoretical potential and promising experimental result, but actually some promising results have been obtained. However, I think currently limitations are as follows. Relational verifiers based on semantic self-composition exhibit increased search cost and reduced efficiency as the capability of representable schedulers grows. So future direction is to leverage various existing syntactic and semantic abstraction, search pruning, and symmetry breaking techniques to accelerate the search. Okay. Okay. I think I have maybe. How much time do I have?
20 minutes.
20 minutes.
10 minutes.
10 minutes. Thank you. Okay, let me then briefly explain the entailment checking in MuCLP, first order fixed point logic. So please recall the slide I presented before, which claims that relational verification boils down to entailment checking in MuCLP, a fixed point logic. Let me use an example. Function program and its relation specification. These are two versions that implement multiplication, which the second one is an optimized version by tail call optimization. Okay, and this is the relational specification of mult and multac. Our tool can automatically prove this one, and these function programs, verification problems, relation verification problems can be reduced to CHE solving problem. But existing CHE solvers cannot solve this one because separate analysis of predicates P and Q involves nonlinear arithmetic. Okay, this part, multac corresponds to Q, and assertion corresponds to this one. And so CHE solving can be reduced to entailment checking in a fixed point logic. So this slide exemplifies the reduction. The right-hand side CSC is satisfiable if and only if the following entailment holds in a fixed point logic. So P and Q are defined using the least fixed point operators, which represent the least fixed interpretation of the definite clauses. And if these two imply the goal property, then CHC has a solution, and vice versa. Okay. So this slide formally defines our fixed point logic, but this is not relevant to the rest of talk. I will skip this. And so the entailment checking, and we have presented an inductive proof system for entailment checking in the fixed point logic. This one, we prove this one, entailment, by induction on derivation of the definition of P. Here, this is the principle of induction of derivations. When we prove that property psi holds for derivation D, we can assume psi holds for all strict subderivations. We will use this principle to prove this relation property. Okay, so this one, home clauses are reduced to inductive theorem proving. And here, this is our judgment. This part represents a set of induction hypotheses and lemmas, and these are premises. Okay, we first apply induction rule to the predicate P and obtain an induction hypothesis of this form. And this part represents a guard to avoid unsound application. Okay, and then we next apply unfold rule to the predicate P and perform case analysis on the last rule used to derive P. And we obtain two subgoals. I think that, yeah, and in the subgoals, to prove the subgoals, we can use the induction hypothesis. they can, so let me try to prove this one, the first one, which is actually easy. We can unfold Q to obtain these two subgoals, but they can be automatically discharged by using an SMT solver. Only interesting case is the combination of these two rules. Here, let me skip the not interesting cases. Here, we have this subgoal when we apply these two rules to P and Q. Here we have recursive occurrence of P and Q, but with different arguments. We can here apply our induction hypothesis to discharge these two, to replace these two with this pure formula without predicate. So induction hypothesis represent relational invariant here, and we can apply relational invariant to close the proof. Finally, we can use an SMT solver to discharge the proof obligation, and we are done like this. And our approach is sound. If the goal is proved, the original constraints have a solution, and it's relatively complete. If the CHE have a solution expressive in the background theory, then the goal is always provable, and so on. And we have automated induction. We use the following rule application strategy. We repeatedly apply induction hypothesis until no new premises are added, and then apply valid, which is an SMT solver, whenever a new premise is added to close the leaves. And we select, otherwise we select some predicate in some heuristic manner and apply induction rule and unfold. This simple strategy is adapted in our tool. And for closing a proof branch, we applied valid rule, where we use SMT solvers, which is powerful, which provides efficient and powerful reasoning about reasoning power for data structures, integer reals, and so on. And we can also use CHE solvers to discharge some of proof obligation, which can handle inductive predicates as well. We have implemented in our tool music, which is available from the web interface. So our tool currently supports entailments expressed in the fragment corresponding to CSCs. And entailment of this form can be handled. Furthermore, we can handle entailment of this form, where the head is replaced by the least fixed point, inductive predicate, which is clearly a strict generalization of CHC. And this is actually useful for program refinement verification and providing lemmas to prove entailments in the CHC fragment as well. And actually, we have done so for commutativity proof of MUD. I have used lemma. Oh, can you see that? Anyway, yeah. So I used lemmas of this form. We have proved them and used these lemmas to prove relational verification problems. Okay. And yeah, our solver can prove and exploit lemmas which are user-supplied, heuristically conjectured from the given constraints, or automatically generated by an abstract interpreter. And our tool can generate a counterexample, if any. Okay. So I think I'm running out of time, so I'm going to wrap up. Okay, experiments and discussion. So the integration of SMT solving, CSC solving, and inductive theorem proving resulted in an automated relational verifier that can verify relational properties across programs in various paradigms, advanced language features, and side effects. And but however, the current limitations are these two. It has limited support for automatic lemma discovery and goal generalization, which are necessary to, for some examples. And it doesn't support the full fragment of fixed point logic. So future directions is to generalize recently observed connection to co-inductive improving to invariant and ranking function synthesis and software model checking to the full fragment of the fixed point logic. Okay? And these slides show the current limitations of both approaches. It often becomes impossible to establish program refinement and equivalence when there is movement of statements across loops or recursions. Examples include loop invariant code motion and loop interchange, loop fusion, which are problematic. So using commutativity or idempotency at the right times may help establish program refinement or equivalence, but more research is clearly needed. Okay, and so ongoing and future work as follows. We have developed a general theory. So we need to develop a general theory and algorithm for aligning reordered executions. And we need to improve the efficiency of semantic self-composition by incorporating abstraction, pruning, symmetry breaking. And interesting directions are to automate relational entanglement checking in the full class of the fixed point logic. And I'm also interested in temporal relation properties and probabilistic relation properties. Okay, so this is the conclusion. Okay, relational verification amounts to synthesis of relational invariants and schedulers, and emerging semantic self-composition techniques enable precise alignment, but requires further development to be refined into an efficient tool. An alternative approach I presented is based on entailment checking in a fixed point logic, first order fixed point logic. It shows some promise, though it requires more automation through the adoption of software model checking and other techniques to fully realize the potential of this approach. And in both automated approaches, aligning reordered executions remain a challenge. Okay, and yeah, the last slide. I'd like to acknowledge this talk is mostly based on these two papers, and I'd like to acknowledge my collaborators, Tachio, Eric, and my former students. Okay, and okay, that's all. Thank you very much for your attention.
Thank you very much for the talk. Interesting. Questions? Yes.
So your example talks did not contain procedures. Can you handle programs with procedures?
Oh, actually, the mount function can be considered as procedures. This one. So I have implemented a relational verifier for higher order functional programs, or CAML, which contains recursive functions. Sorry, this example.
So then you infer summaries?
Oh, yeah, infer summaries. So this one, predicates P and Q represent the post condition of the function, which summarizes the input-output relationship.
Can you handle integer overflows?
Actually, so the second approach is based on SMT solvers for reasoning about data structures. So if the underlying SMT solver supports some overflow and floating point stuff, then our method can also deal with it.
I have a question. So you mentioned simulation in the beginning. Is simulation expressible somehow as a constraint on clauses? Or?
Okay, so your question is how to encode simulations as constraint Hom clauses.
Right.
Actually, I think constraint Hom clauses is not expressive enough to encode simulation. So we have extended the class of CSCs to we called PFW CSP, which kind of support existential quantifiers or Skolem function synthesis, which are needed to deal with simulation.
More questions?
So you mentioned verification of high-order programs, and I was wondering, what about effectful programs, like especially when there is like dynamic allocation or this kind of problems?
Dynamic allocation. You mean stateful programs?
Yeah.
Oh, it's a hard question. So currently, our tool doesn't support mutable states. But yeah, so our tool is based on dependent refinement type system, and we are currently extending the dependent refinement type system to effective programs. We have recently extended our refinement type system to delimited continuations and algebraic effects. So my collaborator will present that work at Popo, so please come. And but we have not yet worked on stateful programs. Maybe we'd like to support them by using ownership types or something like that. But yeah, it's a future work. Thank you.
Thanks.
I mean, I want to say first that I think you have your hands full, even without all the memory stuff. So there's plenty to occupy you. My question is that you talked about aligning reordered executions. I'm sorry I missed the early part of your talk. Is this what, in classical verification literature is referred to as automatically finding a simulation relation between two different transition systems? Or is it different somehow?
Actually, so I'm not familiar with that area. So maybe that classical result can be applied to this one. But yeah, but for synthesizing NGX scheduler, I'm not sure what are challenges there. But yeah, thank you for the comment. Clearly related.
Final question? Okay, if not, let's thank Hiroshi again.
Okay, thank you very much.